Hi guys, it's Miss Nichols here, trying to get the video lesson I promised out to y'all. This is my 6th time recording this lesson, so hopefully it turns out. Okay, I'm looking at worksheet 5, and I have scrolled down a little bit so you can't see the top part, but don't worry, I remember what it says. We're going to talk about converting a position time graph to a velocity time graph, as well as area under a velocity line and stuff like that. Okay, let's get started. First things first, I think drawing would be really helpful for this, so let's take a screen sketch. Fantastic. Let's draw our motion first. So we know that we're starting off at 2 meters, and then in 4 seconds, that's a 3, in 4 seconds, time is in seconds, position is in meters, we have gone an additional 6 meters. So 4, 6, 8 meters. Great. So we've gone there to there. Now let's draw our line. I'm drawing it long so I can make it nice and smooth. Great. That's our position time graph for this problem. Now we need to represent this motion quantitatively, that just means with numbers, in a velocity versus time graph. Big hint, guys, velocity is the slope of a position time graph. Let's write that down. The slope of a position time graph is velocity. Yay! Let's remind ourselves how we calculate velocity. We know that velocity is our displacement over time. And displacement is our final position minus our initial position over time. So in this case, we have gone from 8 meters as our final, and our initial position is 2, and we've done that in 4 seconds. So that is going to give us a 1.5 meters per second velocity. Fantastic. Let's put that into our velocity time graph. Now you may notice that our velocity is constant. We only have one slope. So if the slope of our position time graph doesn't change, and it is our velocity, that must mean that our velocity is going to be the same the whole time. So our velocity at 1 second, 2 second, 3 second, 4 second, the same seconds because it's the same object, it will always be the same. Okay? So I'm just going to draw a nice horizontal line. So this is 1, 2, so this is going to be 1.5 meters per second. Okay? Just one horizontal line. Now we're going to write a mathematical expression that represents the relationship between position and time. So looking at this graph again, we want to find our equation for that line. So we're going to use our y equals mx plus b form because it's a linear line. However, we are going to use our real variables instead of these generic ones. So we're going to say x equals our slope, which we already figured as 1.5, x plus our y-intercept, which is 2. Cool. So that's how we could, oh my gosh, did I actually write the x? That's hilarious. All right, I'm going to erase that. It's supposed to be time. X equals 1.5 t plus 2. Great. Now let's find the displacement from our position time graph. Remember, displacement is just final minus initial. So our final position, which is at t equals 3, is going to be about 6.5. And our initial position is at 1 second, which is supposed to be 3.5. Looks about right, doesn't it? I think so. So that's going to give us a final displacement between 1 second and 3 seconds of 3 meters. Fantastic. Now let's go on and find the area under the velocity time graph from 1 second to 3 seconds. So when I say area, I mean from the line just to the x-axis here. So from 1 second to 3 seconds, it's going to look something like this. Any shape that reminds you of? It's a rectangle. So we just need to find the area of that little rectangle. Let's remind ourselves how we do that. We need to find the length and the width and multiply them together. The length in this case is going to be our velocity, which is going to be we'll just say velocity, and our width is going to be time. We need to think about the unit for this area, so let's do the unit part first. We're going to multiply our units together the same way that we're multiplying our variables. So if we were going to do something else, if we had to define something, we would do the same thing to our units. This is called dimensional analysis. Okay, basically means find the unit based on other units. So our velocity unit is meters per second. Our time unit is seconds, so multiply them together, meters per second times second. Same way we would simplify any other fraction, we're going to simplify this one. Cross out the s's and we're left with meters. So the unit for our area must be meters. Yay! Cool. Let's go back to the problem and put in our numbers. So we know that our length is going to be 1.5 because that's the height we have, 1.5 meters per second. And we're going to need to think about our width, which is 2 seconds because we're going from 3 to 1, 1 to 3, 3 to 1, so 2 seconds. So we need to multiply that together, 1.5 meters per second times 2 seconds. It's going to be 3, what's our unit? Meters. Does this look familiar? Does it? What do you think this area represents? What do you think it means? It's our displacement! Yay! Fantastic. Okay, sum up. We have gone through converting a position time graph to a velocity time graph for constant velocity, and we learned that the area under a velocity time graph is displacement, which I will write down over here. Under VT is displacement. Hopefully this little lesson has been helpful for y'all. And yeah, have a good night, guys. Bye-bye.